Yeah. Are you able to hear me and see my screen as full screen?
Yes, yes.
Yeah. We move on to this next session, which is devoted to the idea of the SK regional centers. And during this session, we are going to have three talks. The first one is by me, where I'm going to talk about the plans for an Indian SK regional center and just set the context. And then we have two sets of presentations from our industry partners. One of them will talk about the challenges, the hardware and software challenges behind setting up large data centers. And the other is going to talk about the applications of AI and machine learning technologies uh, to petabyte scale or exabyte sized data sets. So we have an exciting hour and a half lined up for all of you. So let's get started. So in the SK era, and also now in with the advent of other large telescopes, the sociology of astronomy research is fundamentally changing. In the traditional model, astronomers proposed for time on a telescope. They obtained data on that telescope. They transferred the data to their local computer. They analyzed it, and then they wrote the papers and delivered that some science products and so on. In the future, with the data volumes increasing dramatically, you are going to have to change this paradigm completely, wherein the astronomer's local computer gets replaced with some complex interfaces to the virtual observatory. And there is some now new data handling and data analysis middleware that helps the users analyze their data. Much of the storage and the compute happens on the cloud, on high performance compute systems that are remote from the user. And then, of course, the science output stays the same. At the end of it, you want the astronomers to write their science papers and so on. What has fundamentally changed is that now the compute has become close to the data, right? You can no longer afford to transfer large volumes of data out to the local computer. You simply keep it close where the storage is very close to where the computing is, and everything happens over there. And just the final results of the analysis are what is transferred to the user's computer. Uh, so the regional center concept in the SK emerged a few years ago when it was realized that there's going to be a gap between what outputs, the standardized outputs the science data processor will produce, and what the astronomers actually need to do science with SK data. So it was clear that these standardized data products themselves cannot be simply transferred to users. We have to give them an interface through which they can interact with these large data volumes, run additional data processing beyond what has already been done in the science data processor, perhaps run completely different pipelines on possibly intermediate products or raw data products that enter the SDP. And all of these things will require a dedicated facility to provide those resources. So they came up with this idea of a regional center. And the idea was that the SKA will produce about 700 petabytes of data every year from the two telescopes together. So if you have about 7 SK regional centers, they will be able to sort of host 1/6 or 1/7 of that data. And even with that, you're talking of about a data center capable of ingesting about 100 petabytes per year. And this, of course, could increase in the future as new modes are introduced to SK observations that allow us to sort of increase the data rate. So very, very soon, one is going to be talking about exabytes scale data and storage. It was felt that the LHC tiering system, which is part of something known as the WLCG model, This is the worldwide LHC grid, which is a global collaboration of about 170 computing centers in more than 40 countries at different levels. And the mission of this project is to provide sufficient global computing resources to analyze the 50 to 70 petabytes of data that comes out of the LHC at CERN. Okay. And of course, this is a small fraction of what the SK will produce, but this LHC has been turned on for many years now, and it is already producing those volumes of data for several years now. So the many of the ideas behind the SRC concept have been taken from this WLCG model. It turns out that the SRCs are not formally part of the SK Observatory and are therefore not funded through the main budget of the SKA construction. But they're nevertheless essential to generate science, okay, and will have to work in a coordinated manner with assistance from the SK Observatory, and they will also be accredited to the observatory. And what will they do? They will take data products generated by the science data processor and turn them into science. I mean, this is deliberately vague because we don't know exactly what needs to be done to take those STP products and turn them into science. That's something that's being worked on. I'll come back to that in a minute. The SRCs will also provide resources in the form of hardware, software, and user help desks kind of thing. And they will provide these to regional astronomers along with their data processing. And they should also act as a center for domain expertise where users can go to and ask questions about their data and what they can do to improve the data processing. The idea is that the two telescopes will produce their ODPs, observatory data products, which are these sort of standardized data products which have gone through a standardized pipeline with a known provenance and so on. And these data will flow into several SK regional centers. The SK regional centers will offer a common science platform to the user community. So people will log in to the SRCs just like you and I log into our Gmail accounts or whatever. And the distribution of data within each SRC, the kind of processing that is available in each SRC will be transparent to the user. The user simply logs in onto a cloud system, and whatever resources that are needed for the kind of analysis that is demanded by the user are pulled in from the SRCs as they're available. The data themselves required for the analysis may actually be physically distributed across multiple SRCs. That too will get collated together by the science platform. The analysis will be performed and the results will be given to the user. The user will also have access to some visualization tools so that while they're still logged in onto the science platform, they can see the results of their analysis, they can visualize it in various ways. Where will these SRCs be located? This is one possible layout of the regional center network. You probably want to have one SRC in the telescope host countries in Australia and South Africa. There are plans to put one in Canada, and there's plan to put in continental Europe, one in China, and one in India. And what is shown here with all those red lines is the major NREN paths, which means the national research and education networks of various countries have, for the purpose of large collaborations, have already bought underwater optical fiber links across the various oceans. And one will need to tap into those to transfer the volumes of data that we need to for the SKA. And what is also indicated here is the cost of transferring data. So there is something known as a 10-year IRU, indefeasible right of use, which means you sort of uh, commit in advance to, it's like a 10-year subscription to the optical fiber. And you can buy these in 100 gigabit circuit units. So like India might decide to buy an IRU connecting us, let's say, to the UK or to Australia, a 100 gigabit circuit. And if you commit to buying it for 10 years, then this is the kind of prices that you get, which I indicated in black. The network costs are going to be significant, a fraction of the cost of running the SRCs. It is hoped that they will come down with time, but we may be constrained by the cost of network when we design the layout of the SRC. So what will the regional centers actually do? They'll provide an access for resources, okay, human resources, scientific expertise, software expertise, but also hardware resources, computing resources. They'll provide support for scientific development. They will provide subject-specific pipelines. So for example, if there is a key science project, for example, an epoch of reionization type experiment, which requires its own different dedicated pipeline, then those pipelines will be developed within the SRC context, and they will also be resources will be hardware resources will be made more available to him. There will be a common effort for the common software stack for things like visualization, stacking, co-adding software, which will come out of the SRCs. They could also be designed so that they can provide compute resources for simulations related to SKA experiments. They'll provide access to data. So this will be the primary method by which users will get to their data. And there will be the usual security and access policies and so on, which will be incorporated and implemented. And they will play a decisive role in the hosting and distribution of the archival observations of the SKA. They will provide local time zone user support so that if there is one SRC, so you call the SRC helpline or you email the SRC helpline, you will get a response almost immediately if it's in your local time zone. But of course, you will be able, we may have an integrated system so that you can get response from other places as well. Access to proposals, information, training, outreach activities, and so on. There will be a liaison between the SRC network with the SKA Observatory on one side and these national research and education networks. Okay, these are going to play a very crucial role to make available to the SRCs sufficient and affordable network capacity, because we will be moving massive amounts of data. And so, for example, in India, we have something known as the National Knowledge Network, which provides a backbone for data to be transferred between the research and education institutions within the country. And it also has some international bandwidth. So when we approach the NKN, we are going to ask them for not just for the domestic data hall, but also look at getting high-speed dedicated optical fiber links to the other SRCs. SRC makes good sense for us because we have a large community of potential SK users, and we hope that we will be leading a number of key science projects, and each of these key science projects will need to make available significant SRC resources. We are network-wise well connected with both telescope sites. This is indeed fortunate. About 20-25 years ago, during the time of the dot-com boom, there was a lot of optical fiber laid, which was later not used. But there was a lot of undersea fiber that was laid at that time. This is called dark fiber. And India being at the sort of just north of the Indian Ocean. We have fairly good connectivity to Singapore, which has in turn good connectivity to Australia. And we also have through Europe fairly good connectivity to Australia. We have, of course, a large pool of software developers. We need them to develop and maintain a regional center. But to build a data center that ingests 100 petabytes a year and processes it is not a simple activity. This has never been done before in the astronomy domain. So you have to collect data, you have to analyze it, you have to move data, and so on. So every country that aims to build an SRC in their country are taking a limited view at the moment. They're saying, yes, we will eventually build a regular SRC, but right now let's build a prototype. Okay. It will just not have the same size and scale. Sorry for that. So we'll build something much smaller than the SRCs, but it will be functionally quite similar to the full SRC, except that it will have perhaps 1/100th of the data that the full SRC will have. So we've decided in our proposal to the government that we would like to take the same approach, build a prototype SRC, proto-SRC over the next 4 to 5 years, and then build out the full SRC in time completion of the SKA phase 1 when the data really begins to flow. I'll just tell you a little bit about what other countries are doing. China, for example, has already built a proto-SRC. These are their specs of their compute system. Taken together, they already have about 119 teraflops of computing. Their storage is at the moment quite modest, a couple of petabytes, but they're in the process of scaling it up quite a lot. Notice here that they have gone in for a system which has fairly heterogeneous hardware. It has both CPU-based and GPU-based systems. And it is very likely that every SRC will evaluate what their requirements are and what kind of resources they can best provide within their constraints of budget and other things. That the design of every SRC will not be the same. It's likely that it will be quite different. So the idea behind the network is that every SRC will commit to providing a certain level of resource to the full SRC network. So somebody will say that we will provide so many petabytes and so many petaflops of computing over the next 3 years. And then 3 years later, they will change that number. And every country or every SRC will come up with its own numbers, which may change with time. So the Chinese have used a heterogeneous architecture. Okay, they've also used ARM-based, RISC-based machines. What has already come out, and it's not something new that we didn't know about, is that what ARM processors will help out with is with higher memory bandwidth and lower power consumption. And of course, power consumption is always a plus, lower power consumption. But the higher memory bandwidth I'll come back to in a moment as to why that is important. They've also used all-flash NVMe type storage in the Chinese prototype SRC, and that has already led to a fairly large increase in memory bandwidth and IO bandwidth. Okay, compared with traditional clusters. So why is memory bandwidth important? So there is a figure of merit for high performance computing, which is called the arithmetic intensity. So any system that you have should have arithmetic intensity that is well matched to the algorithms that you plan to run on that high performance computing system. So arithmetic intensity is defined as total flops per total DRAM bandwidth. Okay, so it has basically floating point operations per byte is the unit of per byte per second. is the unit of that quantity. Sorry, no, there's no second. Floating point operations per byte is the unit of that quantity. If you take the standard two of the standard algorithms in any radio interferometric processing, grading and FFTs, they are typically rho of 0.5. What that means is that if you have uh, uh, one floating point operation that you perform, typically you perform it on 2 bytes of data. Okay, which means it's fairly IO intensive. There is a lot of memory exchange that happens relative to the amount of floating point operations that are done on those pieces of data. So typical GPU accelerators have rho of 5. So for example, there's a example given here with the NVIDIA Pascal GPU. There's the memory bandwidth and the floating point bandwidth and so on. And if you do that, if you build, for example, a system that is based on these NVIDIA Pascal GPU architecture, your computational efficiency won't be very high because you need a rho of 0.5 for your algorithms to run efficiently. You are given a computer with rho of 5. Since they're not well matched, you're basically using only 10%. You're using the system with 10% efficiency, which also translates to you having to buy 10 times more computers than you would otherwise needed if you had operated at 100% efficiency. This is going to be one of the show-stopping crisis for the SKA. So there are a lot of efforts that are going on already, wherein when the SKA SDP, for example, is working with vendors to try to see how the memory bandwidth can be increased. And it is in this context that the Chinese ProtoSRC results on the speed of NVMe storage is very promising. Of course, this is just the first step. One will have to do a lot more in improving memory bandwidth in order to get the arithmetic intensity that we want. In Europe, there was a very large program called NES. It was a 3-year initiative funded by one of the European Commission programs to develop a fully functional design for a European Science Data Center, which is the European SRC. And it ran for 3 years, 2017 to 19, and they did a variety of design studies where they evaluated various technology options and choices for compute, storage, etc. And they did very careful costing as well by using the manufacturer roadmaps and the costing projections for the future to try and identify technologies that seem most promising for building the SRC within the budget that has been provided. There are a lot of outputs. They've made all their reports public. So if you go to this website that's mentioned here at the bottom, you can download all their reports. And this is just a table which summarizes some of their key findings. Okay, where should be located, what should be the authentication mechanism, what should be the overall framework, and what should be the size of the European SRC, and so on. So this forms a very useful set of documents as a starting point. Canada is getting started. They have a project called CIRADA, which involves pipeline development and product generation for several radio astronomy projects that Canadian astronomers are involved in. They've developed a number of user tools. It's a 6-university collaboration led by Brian Gensler. There are enhancements to something known as CANFAR, which is a science platform and a cloud processing and storage system which offers VO services, database services, machine learning and archiving, and so on. So they're also getting started. And both of these initiatives are now funded for the next few years. So the Canada will see some developments. For the Australian SKA Regional Centre, they have funding of about.
Yogesh, sorry to
Yeah,
interrupt. You have to wrap up in next 1-2 minutes.
yeah. I'll be done in about 2 minutes. Yeah. So they have a design study which has started. They want to get the design study done, and they want to build out an SRC over 2022 to 2023. South Africa is doing efforts, internal efforts in Sarau, providing sort of with a focus on developing new software and new SRC type resources for use with the Meerkat telescope. So what's the situation in India? We don't have a very large data archive. Okay, nothing exists currently. That's on petabyte scales. We are approaching a petabyte of storage for the GMRT data archive, and IUCAA has, of course, set up a large data center for LIGO, and they also have a large data center for processing the MALS data from the Meerkat telescope. So what could the ProtoSRC do? We envisage that there will be three options, sort of three main areas. We could develop and implement a data processing pipeline for the UGMRT data. We'll discuss this in the panel. Then we will develop and implement a pipeline for processing other precursor data, for example, solar MWA data, which Divya Oberoi and his collaborators are working on. And then we could also develop large-scale computer simulations. And there are a number of people on this call who have worked with large simulations related to the SKA, and those could be funded. So what have we asked for? We have asked for funding for a proto-SRC for the next 5 years and a full SRC after that. The proto-SRC will cover the construction of a suitable data center and also for managing these. We will we hope to get high-speed internet connectivity for the proto-SRC through access to NKN. That should be sufficient. But for the full SRC, we will probably need to purchase IRUs connecting us to the full network. I think I'll skip this. There is a great opportunity for international collaboration here. Everybody's facing the same problems. So we expect to have extensive collaboration with other SRC efforts. The collaboration can be enabled and coordinated centrally. So the SK Observatory now has something known as the SK Regional Centre Steering Committee, and that could help in coordinating the activity across the different countries. Also, the steering committee has set up working groups to define the requirements of the full regional centers and develop an architecture and so on. Some months ago, I had solicited volunteers from the India SK Science working groups. Now we have 5 people who are now members of the SRC working groups. Okay, so I'll stop now and take your questions.
Thanks, Yogesh. So let's take a couple of questions if there is any quick question from the Zoom. I see Abhirup has a raised hand. Abhirup?
Yeah, am I audible?
Yes.
Yes.
Yes. Thanks, Yogesh. I may have missed it. So, as SRC activity, I mean, how does this scale with the NSM activities, which is also parallelly going on? And
yes,
essentially, certain parts of the both are kind of common, but definitely we have some exclusive portions of the SRC which may not be general, like
yes,
the storage of the huge data. Yeah. So have we explored that?
So we have not formally contacted them and explored those possibilities.
Right.
They're, as I pointed out, they are building what are called more traditional HPC computing.
Right.
What we want is something which has a much different arithmetic intensity. And this is referred to as high performance data analytics computer. So HPDA rather than high performance computing. So our requirements will be fundamentally different. We are also a bit concerned about how the funding channels will work, because I think this is uh, basically Ministry of Education money now that funds the National Supercomputing Mission. Uh, so we did not see that many synergies that we felt that we should connect up with them. That's why we have not done that, and we put in a separate funding request in our detailed project report, asking for a dedicated SRC for the SKA. Okay, we have talked about in our proposal of the possibility of sharing these resources with other astronomy projects. Okay, even outside of radio astronomy or within radio astronomy, but we have not talked so much about a very general system, because I think our system is going to be a very specific system that is tailored to work well with SK data. So I don't know, Yashwan, do you want to add anything about from the NSCM aspect?
Yeah, I think it's an interesting point to consider whether the National Supercomputing Mission, and I think that is what is being referred to, is, I mean, it is meant more for providing general purpose computing platforms, though there are special application groups which are being talked about and discussed. Actually, there is some kind of a proposal that is in there for supporting possibly some real-time computing at GMRT, which is again a special case of generalized computing. But that's a side topic. And so in some sense, what we need, I mean, there may be synergies in terms of learnings with what NCSM is doing, but whether directly it can be part of NCSM is probably difficult, especially given that this is going to be part of the SKA project and would come from a different stream of funding. So there are some aspects there, because at some level the NCSM funding stream is exclusive. I mean, it sort of excludes funding to DAE supported institutions, and so there are some issues, some aspects there. But certainly there is a lot of push for next generation computing, and there's definitely synergy in terms of things that we can learn. I mean, and then later when we talk about AI and ML, again, there are national level initiatives where again we've been encouraged to synergize. And so synergy is definitely, I think, possible and expected. But I don't know whether there's, I mean, I'm not sure about a common funding stream.
Okay. Yeah, thanks.
There is one more quick question, maybe the last one before we move to the next talk. So just for curiosity, this is question from Jitendra, who has just sent a DM to me. Just for curiosity, will SK science PI team share data immediately to SRC before exploring their science goal? Yogesh, do you know anything about this?
No, so I can respond to that. Am I audible?
Yes.
Yeah. So see, the way the the KSPs will be organized is that they will, just like we have for GMRT data, we say 18 months after the data are taken, they will be released publicly. So when they are released to the SRCs, they will not be public to other users. So the KSP PIs will use the SRC resources to process their data through their own pipelines. Okay, these will not be available publicly. They will be physically sitting in the SRC, but they will be available to the members of each KSP team. So they'll have access. The team will have access, but not the general public. Of course, there will be a certain proprietary period. Once that is over, they will become completely accessible to the public.
Okay. Yeah.